Welcome back to the third video lecture of vector space. In this lecture we are going to talk about linear span and linear dependence and independence. So let's start with linear span. What is linear span? Suppose I have a set, let's say, and set S is given to me, and this is simply a set, not a subspace or a vector space. So inside a vector space V, I have a small set S, and containing the set S, I want to create the smallest subspace possible. Imagine this is the smallest subspace which contains S. Okay, so this is the smallest subspace containing S. Then this subspace that we have created, it is going to be called L of S, which means linear span of the set. So we represent linear span of any given set S by the short form L of S. So the definition being L of S is the smallest subspace containing any given set. Achha. So this is the actual definition. And now let's look at what are the kind of elements L of S contains. LS contains, let's say, let me define first that the S set contains the element alpha 1, alpha 2, alpha n. These are the elements in the S set. Then LS set would contain C1 alpha 1 plus C2 alpha 2 plus Cn alpha n, such that all the Ci's, they belong to field for all I equals to 1 to n. So basically it's nothing but linear combination of the elements of the S set. So I've taken all possible linear combinations of the S set, and I have formed a set with those all the linear combinations, and that is called L of S, which is the smallest subspace containing S. Okay. So now let's take a look at this theorem. Okay, before we go into this theorem, I have a few more things to say about linear span. Suppose my S set is an empty set. Okay, it does not contain any elements like alpha 1, alpha 2 does not contain. It's simply an empty set. Then as per definition, L of S would contain only the theta element, which is the null element. That means the identity with respect to addition. The identity element that we have in vector space with respect to addition, which we represent as theta, or the null element. So LS would be theta, only the set containing theta, provided if my S set is completely empty. So this is a definition in linear span, and we consider this whenever we are constructing LS. Okay, so now I'll again go back to the theorem that I was talking about, that I have two sets, non-empty, not empty, both are non-empty, S and T, and they are both finite sets. So they are not infinite, they are finite, of a vector space over a field F. And this is the important information given to us, that the set S is a subset of the set T. If this is happening, then we need to prove that L of S will be a subset of L of T. Okay, so we have, if S subset of T, then LS has to be subset of LT. Okay, so let's try to understand what's happening here. Suppose I have the vector space like this, and this is my vector space V. I have the S set and a T set. The T set is a larger one. Let me draw it a little bit small. Let's say this is my T set, and let's say this is my S set. So I have two sets, S subset of T. Then what I need to draw is, if this is L of T, then this has to be something L of S. So obviously you can see L of t contains the entire t set, and L of s, it contains the entire s set, not necessarily the t set. Okay, L of s will not contain, it is not necessary for L of s to contain the entire t set. It may contain, it may not contain. So in general I have drawn it in such a way that it does not contain the entire t set. Okay, so we have to show basically that LT, which is the blue set which I have drawn, is a larger set, and the green one, which is L of s, is lying completely inside it. That means L of s subset of L of t. Okay, so this is something that we have to prove. Okay, so let me just erase off whatever I have drawn. So what we are going to try to do is, whenever we try to show that A subset of B, okay, talking about set theory, whenever we try to show one set is subset of another, what we do, we take a random element from here, let's say alpha, we take a random element and try to show that this element also belongs to the other set. If we are able to show this, that means what I'm trying to say here is, if alpha belongs to A, if that implies alpha belongs to B, then we can say that A is subset of B if alpha was taken arbitrarily from the set. Okay, so the concept is, I'll take some random element from the L of S set, okay, some random element alpha, and I will try to show that this alpha belongs to the L of T set. Okay, so this is what we will be trying to do. So now first of all, let me define the S set, that let S contains the elements alpha 1, alpha 2, dot 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 alpha n. Since it is non-empty, that's given to us, so I have constructed the S set in this manner. Okay, so now let me construct the LS set, or no need to construct the LS set, I'll just try to take a random element from the LS set. Now you already know how does elements of L of S look like. L of S looks like linear combination of the elements of the S set, right? So if I want to take a random element alpha, okay, I'll not name it alpha, just for convenience sake let me name it something different. Let's say I'm calling it eta. Okay, so I'm saying that let eta belongs to L of S, so that means eta would be looking something like a linear combination of the elements of S. So that means, let's say R1 alpha 1 plus R2 alpha 2 plus dot 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 Rn alpha n, where all the Ri belongs to F for all I equals to 1 to n, right? So I have chosen a random element from the LS set and I'm calling it eta. Now my target is to show that eta will also belong to the LT set. Okay, now how am I going to do that? You can see S is subset of T. That means all these elements of S that I have taken, they definitely belong to the T set, because T contains all the elements of S set. Okay, so alpha 1, alpha 2, dot 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 alpha n, all these elements belong to the T set. The reason being T contains all the elements of S set. Okay, now as we know that linear combination, we have done this in the previous lecture, that linear combination of elements of any set, it forms a subspace, and we have proved that in our previous lecture. So again I can come back over here and I can say, when I was defining linear span, I can say that linear span of any set is always a subspace, right? Always a subspace, and it is basically the smallest one, right? It is basically the smallest subspace which contains the S set. So it's always a subspace by default. Okay, so L of T is also a subspace in that case. So we know L of T is definitely a subspace and it's the smallest one containing the T set. But our important thing is it is a subspace. Okay, so if alpha 1, alpha 2, alpha n, all these elements belong to T, then all these elements definitely belong to L of T also. because each element is a linear combination of itself. Now how could I say that? This is a very simple observation which you can make. Alpha 1 can be written as 1 times alpha 1 plus 0 times alpha 2 plus 0 times alpha 3 and so on 0 times alpha n. So you can see alpha 1 has been expressed as a linear combination of all the elements of the S set, where I've taken all the constants here to be 0 except for the first one. So definitely alpha 1 is a linear combination of all the elements of S set, or in this case I can say that alpha 1 is a linear combination of all the elements of the T set, and hence alpha 1 is going to belong to L of T. Similarly, alpha 2 can be expressed as a linear combination of all the elements of the T set, and therefore alpha 2 also belongs to L of T. And similarly, all the elements of the T set definitely are going to belong to L of T. Now we could have told this from another logic also, another simple logic which I was explaining over here, that L of any set contains the set itself, right? So if L of any set contains the set itself, then over here I can easily say that the elements of the T set are definitely contained inside the L of that set. So that we could have said very easily. Okay. So here I could just write this particular logic, that since LT contains the T set. Okay, so all these elements belong to LT, and I know that LT is a subspace. Okay, so if LT is a subspace and LT contains all these elements, then simply by the subspace property, by the property of subspace, R1 alpha 1, R2 alpha 2, Rn alpha n, all these elements are also going to belong to LT. This was the second criteria of something to be a subspace. Any constant multiplied with the element of the set is also going to belong to that set. Then that set could qualify to be a subspace, right? So here, since LT is a subspace, if I multiply all the elements of LT with some constant R1, R2, Rn, then that also has to belong to LT, right? And now again, using another property of subspace, that if I take two or more elements from a subspace and if I add them, they're all going to still belong to the subspace, right? So that means if I take all these elements from the subspace alpha LT and if I add them, they are still going to belong to LT. So that means R1 alpha 1 plus R2 alpha 2 plus Rn alpha n, they are all going to belong to LT. So these two things we could say only because LT is a subspace. So here I can say that since LT is a subspace. Okay, so you can see this element is nothing but the eta element that I have created over here. Okay, so the eta element has been created. So I can say that therefore eta belongs to L of T. So initially I had started the proof by saying eta belongs to L of S, and I have reached the point where I have got eta belongs to L of T. Okay, so that means now I can connect the dots and I can say that therefore eta belonging to L of S implies eta belonging to L of T. Now as I told you before, this using the simple property of sets, we can say that L of S must be a subset of L of T. So and hence that is proved, right? So this is what we wanted to show. So now remember this theorem as a statement. This will be very helpful for us, that whenever we have S subset of T, if I take the linear span on both the sides, imagine taking an L, writing it like this, taking an L on both sides, the subset symbol is still going to be satisfied. Okay. So now moving on to our next theorem. This is a little bit confusing one, although it's very easy if you understand that S, if it is a non-empty subset of some vectors of vector space V over a field F, then linear span of S, L of S is nothing but same as L of S. Okay. Now here, before I start this thing, keep this in mind, very carefully keep it in mind that Ls is the smallest subspace containing S. Okay, this was the definition of L of S. Now let me write this in a way that will be easy for you to understand this theorem. Okay, I am writing it in a little bit easier language. L of box. Okay, now imagine box is anything that you want. Okay, anything that you want is box. It can be S, it can be any other thing, doesn't matter. L of box is the smallest subspace containing the box, right? So you can relate the line that I have written here with the generalized format that I am trying to write over here, that L of anything, any box, anything means in this case any set, is the smallest subspace containing that particular box. Okay, so if you keep this in mind, now let's see what is going to happen with L of S. I can treat this as my box, right? I can say this is my box. So L of box, it is the smallest subspace containing the box. So that means I can say that L of S is the smallest subspace containing which one? Containing the box, right? And what is in the box in this case? In the box we have Ls. So containing L of S. So L of S is the smallest subspace containing L of S. Okay. Now again we know that this L of S that I have got, L of S is a subspace. Okay. This is something that we already know, that L of any set is definitely a subspace. So I have got L of S is the smallest subspace containing Ls, and Ls is itself a subspace. Now see, this word is actually creating the problem. Concentrate on this word. L of S is the smallest subspace which contains Ls. Now Ls is itself a subspace, and the smallest subspace containing Ls is Ls itself. What I am trying to say here is L of S is the smallest subspace containing S, and the smallest subspace containing Ls is nothing but Ls itself. Because if suppose, imagine this figure that I am drawing, this is a vector space, this is some subspace, okay, this is some subspace, then the smallest subspace containing this subspace is nothing but the subspace itself. Is that logic clear? The smallest subspace containing this subspace is the subspace itself, right? So therefore the smallest subspace containing Ls is the set Ls itself, because Ls is a subspace, right? So that means L of S is nothing but Ls. Okay, so that's a simple logic. So now you can understand, if I take thousands of L of like this, if it goes on, and S, so how many L I take doesn't matter, it's still ultimately going to be L of S. Okay, so keep this thing in mind. So how many times you take L of any given set, it's ultimately going to be same as L of S. Okay. So now let's get to our next theorem, in linear span, it is saying that S and T are non-empty subsets of a vector space V over a field F, then this is something that we have to prove, that L of S union T is equal to the linear sum of Ls and Lt. Okay. Now, why did I use the term linear sum? You can remember from our previous lectures that if S is a subspace and if T is also a subspace, then S plus T, this is also a subspace, and this subspace is called the linear sum of S and T, and the linear sum forms a subspace and it is the smallest subspace containing both S and T, right? This was something we have done before, so I will not go into that. So here in this case, Ls is a subspace itself, Lt is a subspace itself, so sum of two subspace is nothing but linear sum. Okay, so now I won't try to draw the Venn diagram for this. Again, simple logic. If I have to show that a set A is equals to a set B, how do we show that two sets are equal? The first thing that we try to show is A subset of B. The second thing that we try to show is B subset of A. So if both these things are satisfied together, then we can say that A is equals to B. Now, how do we show that A is subset of B? We take an element from here, let's say alpha, and show that alpha belongs to the B set. And again, for this case, we take some element beta and show that beta belongs to the A set. So this is the process of showing that two sets are equal. So here also I have two sets, one on the left hand side and one on the right hand side. So I want to show that this left hand side is a subset of right hand side, and right hand side is again a subset of the left hand side. Okay. Achha. So first let me try to show that the right hand side is a subset of the left hand side. Okay. So remember what I'm trying to show. I'm trying to show that Ls plus Lt is a subset of L of S union T. So this is what I'm trying to show at first. Now in order to show this, I need to take some element from here, let's say eta, and show that it belongs to L of S union T. So in order to do that, first I need to define my S set and T set. Okay, now it is given to me that both are non-empty subsets of the vector space. So let me define that, let S equals to alpha 1 alpha 2 dot 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 alpha n, and T equals to beta 1 beta 2 dot 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 beta n. Okay, and similarly S union T will be combination of, or actually collection of, all the elements of S and all the elements of T. So I'm not writing that. Okay, so now I'm going to take an element from Ls plus Lt. So let me define that, let eta belongs to Ls plus Lt. That means eta can be expressed as, let's say, gamma plus delta, kind of a structure where gamma belongs to Ls and delta belongs to Lt, right? So that means gamma must be linear combination of the elements of S. So if gamma is a linear combination of the elements of S, then gamma must be looking like R1 alpha 1 plus R2 alpha 2 plus Rn alpha n for all Ri belonging to F. And similarly, delta, if it is an element of Lt, then it must be linear combination of the elements of T. So I can write delta equals to S1 beta 1 plus S2 beta 2 plus dot 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 Sn beta n for all Si belonging to F, and I equals to 1 to n for each of the cases. Okay. So now one more thing you could have said, that why is the cardinality of S and T both same? Why are they both n times? Now that's not necessary, because these are simply two non-empty subsets. So I'll make my approach more generalized. Okay, let me improve my approach. Instead of taking n number of elements in the T set, let me make it m number of elements, where n may be equals to m or may not be. Okay, so that means over here I have to make it Sm and beta m, and in this case for the first one I will have I equals to 1 to n, and for the second one I will have I equals to 1 to m. Okay, so I have changed the cardinality of the sets to make it more generalized, to make our approach more generalized. Okay, so I have taken gamma and delta. So now basically I have the eta element. Eta is the addition of these two elements, and I need to show that eta is going to belong to L of S union T. So let's quickly check out eta. So eta would be gamma plus delta, that means the sum of these two things. So I will write the sum for you. It's going to be R1 alpha 1 plus R2 alpha 2 plus dot 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 Rn alpha n. So the first row has been taken. Now come to the second one, plus S1 beta 1 plus S2 beta 2 plus dot dot Sm beta m. Right, so I have taken the sum of gamma and delta. Now you can observe this line that I have written. This is nothing but a linear combination of the elements of S as well as the elements of T. So this is a linear combination of the elements of S and T. That means the linear combination of the elements of S union T. So I can say that this belongs to L of S union T, because all the elements that I've circled here, these are the elements of the S union T set, and since this is a random linear combination, so that means it must be belonging to L of S union T, right? So I have got eta belongs to L of S union T. So this was our first thing that we wanted to show. So that means I have started from eta belongs to Ls plus Lt, and I have reached eta belongs to L of S union T. So from here I have reached here. So that means I have that therefore eta belongs to Ls plus Lt implies eta belongs to L of S union T. So this would together mean that Ls plus Lt is a subset of L of S union T. So that's our first part. So similarly I have to show the reverse part as well. Okay, now to show the opposite thing is also happening, we can make some simple observations that we know Ls is a subspace that contains the S set itself. So that means we know S is a subset of Ls. So from here I can say that S is also a subset of Ls plus Lt. So if I add something, it's still going to be the same because I'm just increasing the size on the right hand side. So it's still going to be a subset, right? Again similarly, T subset of Lt, and again I can increase the right hand side by adding L of S. So that means T subset of Ls plus Lt, right? So I can see that S and T are both subsets of the same RHS that I have written. So together these two would imply that S union T is subset of Ls plus Lt, right? Because S and T are both subsets of the RHS, same RHS. So that means the union of S and T, that will be also a subset of the same RHS, right? Now S union T is a set, and the right hand side, that's a subspace. So I can say that L of S union T, that is subset of L of Ls plus Lt, right? This is coming from the previous theorem that I have done. That means this one, that S subset of T would imply LS subset of LT. So from that theorem I have L of S union T subset of L of the right hand side, right? Now coming to the previous theorem, here I have shown that if I take L of a vector space, that means this part was this inside part, this was a vector space, right? So if I take L of vector space, I will get that same vector space as my answer, right? That's why L of S was the LS itself. L of any vector space is the vector space itself, right? So over here, as I told you right at the beginning, that this is a subspace and this is a subspace, and their addition is the linear sum, and we have done before that linear sum is a subspace, right? So the right hand side, this inside part, it's a subspace, that means a vector space. So L of a vector space is simply the vector space itself, that means LS plus LT using the previous theorem. L of any vector space is the vector space itself, just coming from the previous theorem. So hence this is the second part. So I have done the first part here, which I was calling as 1, and this is the second part. So 1 and 2 together, they would imply 1 and 2 would imply L of S union T equals to LS plus LT, and that's the proof. Okay. So then coming to the next part, which is linear dependence and independence. Suppose I have a set of vectors S given by alpha 1, alpha 2, dot 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 alpha n, and I want to examine whether this set is linearly dependent or independent. Okay, now let's first get the formal definition done. If this set S is linearly dependent, then for whether it is dependent or independent, first I'll take a common statement that let some constant into alpha 1 plus some constant into alpha 2 plus dot 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 some constant into alpha n is equals to the zero element, which is theta. Okay, so let me consider this statement. Now from here I will develop two definitions. One is of linear dependence and one is independence. Okay, linear dependence I will represent by LD, and linear independence I will represent by LI. Okay, so now the set S is going to be linearly dependent if C1 equals to C2 equals to dot 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 all the constants are specifically 0. Okay, in this expression, if all the constants are specifically 0, that means you can see if C1 is 0, C2 is 0 and Cn is 0, all the constants on the LHS are 0, then the entire LHS automatically becomes theta, and right hand side is also theta. So the equation is satisfied by this solution where all the constants are 0. If all the constants are 0 is the only solution of this equation. Okay, it's the only solution. So if this is the only solution, let me call this equation as 1, is the only solution of 1, then I'll just need to interchange this two. I just gave you the definition of linear independence. Okay, so the set is linearly independent if all the constants are specifically 0. Okay, and that is the only solution of equation number 1. So this is called basically the trivial solution, because if all the constants are 0, it automatically satisfies the equation. So this solution is always going to be there no matter what. But other than this one, if there exists some other possible set of solution, that means now if another different set of solution is existing, that means at least one of the constants has to be non-zero, because if all the constants are 0, that's one solution and that has come into this category. Now if there exists an alternate solution to this, then at least one of the constants has to be non-zero. So if at least one of Ci, okay, for whatever index I, is not equals to 0 for any I equals to 1 to n, then this set S, this set of elements is going to be called as linearly dependent. Okay, so these are the two definitions of linearly dependent and independent sets. But now here you should observe one thing or remember one thing, that in linear dependent, in case of linear dependent, if all the constants are 0, that still satisfies equation 1. That means all constant 0 is a solution. But other than that, at least one constant non-zero is also a part of an alternative solution, and if that is possible, then the set is called linearly dependent. And if all the constants has to be mandatorily 0 and that's the only solution of system 1, then we will say that this given set is linearly independent. Okay, so this is the concept of linearly dependent and independent sets. Now a few important observations or conclusions I need to make here. Number one, and the superset of a linearly dependent set is linearly dependent. Okay, that's one observation. I'll just come into the proof of that right now. And number two, the subset of a linearly independent set is linearly independent. Okay, so these are very two important observations. First, let me talk about the last one, that the subset of a linearly independent set is still going to remain linearly independent. Acha. That means, first, instead of proving this one, let me prove the first one. Okay, that would be easier. The superset of a linearly independent set is going to be linearly dependent. That means if I have a set S and if this set is linearly dependent, then superset means if I increase the size of the set, if this is the T set, then T is a superset of S, then T also has to be linearly dependent. So if I increase the set, increase the size of the set containing the previous one, then the set is going to remain as linearly dependent. Acha. Let's say that let S is linearly independent as per the figure I've drawn here. Okay, so suppose S contains the elements alpha 1 to alpha n, so that would mean that C1 alpha 1 plus C2 alpha 2 plus dot 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 Cn alpha n equal to theta, and that would imply at least one Ci is not equals to 0. Okay, just let me consider that specifically the ith index is non-zero. Okay, specifically the ith index is non-zero and rest of the constants are 0. Okay, so let specifically Ci not equals to 0. This is just for the sake of understanding I am writing. It may happen that there are more number of constants which are non-zero. Just for the sake of understanding, let me consider that specifically Ci'th index is non-zero. Okay, so then in this expression that I have written, there is some Ci over here, Ci alpha I, where the Ci index is non-zero. Inside the dot dot there is some specific Ci such that its constant, the Ci, is non-zero. Okay, now imagine that alpha or T contains the set alpha 1, alpha 2 dot 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 alpha n, and there are few extra terms which is alpha n plus 1, alpha n plus 2 dot 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 alpha r. Okay, so these are the extra elements contained in T. The previous ones are coming from S itself. Okay, so now imagine this expression, that C1 alpha 1 plus C2 alpha 2 plus dot dot dot, somewhere down the line I have taken Ci alpha I plus dot 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 reaching Cn alpha n, plus now consider the new elements which I am writing, 0 into alpha n plus 1 plus 0 into alpha n plus 2 plus dot dot 0 into alpha r. So now will there be any change in conclusion? Just check that this part up till here, it's same as the previous line, and I have taken that to be equal to theta. So this part is theta. Now these constants I have taken strictly 0, so that means the entire expression remains same as the previous one, and this is still going to be theta. Okay, so it's not changing, where specifically the Ci is non-zero. So in this expression you can see I have written the linear combination of the elements of the capital T set, right? These are all the vectors of the capital T set, alpha 1, alpha 2, up till alpha n, then going on forward alpha n plus 1, alpha n plus 2, up till alpha r. So these are all the elements of the T set. When I take a linear combination of that, I get theta, where specifically the Ci constant is non-zero. So that means the set T is linearly dependent. It's satisfying the condition of linear dependence. Okay. So this is the idea, that if I take a superset of a linearly dependent set, it again turns out to be linearly dependent. Okay, it does not become independent. So if I increase the size, a dependent set keeps on remaining dependent, its nature doesn't change. Now exactly in the same way, if I reduce the set, okay, if suppose my starting set is a linearly independent set, and if I take more and more subsets of that, it's still going to remain independent and it's not going to become dependent. Okay, now this proving this can be very simple actually. Using the previous thing, I can just prove it very easily. I can use some method, contradiction method like this, that let S be linearly independent and T be the subset of S. Okay, so now the thing is looking something like this, that this is my S set which is linearly independent, and this is my T set, and I want to show that T is also linearly independent. Okay, I have taken the subset. So S is linearly independent, I have taken a subset which is S, subset which is T. Okay, so now you can observe that if by chance T becomes dependent, if T is dependent, then see what will be the problem. Now think it in the other way round. If T is linearly dependent, then S is a superset of T, right? S is a superset of T. So if T is dependent, we have already proved over here that if I take the superset, a dependent set has to remain dependent. So here I can see if by chance T is dependent, then its superset is becoming independent, which is a contradiction to this first proof that I have done. So that's not possible. So that means T has to be linearly independent and not dependent. Okay, so if T is dependent, then it contradicts the previous theorem that we have done. Okay, it contradicts the previous one, so therefore it implies T must be linearly independent. Okay, so again I'll sum up what we did, that if I take a subset of a linearly independent set, so I already have a linearly independent set, if I take its subset, it's still going to remain linearly independent, and if I take the superset of a dependent set, it's still going to remain linearly dependent. The opposite things we can't say anything. Okay, like if I take a subset of a linearly dependent set, I don't know what will happen. Okay, so I have a linearly dependent set, I'm taking a subset, it may be dependent, it may be independent, it's completely depending on the choice of the elements. Similarly over here, if I take a superset of a linearly independent set, we don't know what it will be. It may be independent or dependent, completely depending on the choice of elements. Okay, so the opposite things, we don't know anything about them. And one more important observation or note that we need to remember, that a singleton set means a set which contains a single element. Okay, which contains a single element. That can be the zero element also, okay, that can be the theta element also, no problem with that, but any single element, that's called a singleton set. A singleton set is always linearly independent, okay. So by definition, a linearly independent set is always going to be linearly independent, okay. So this is all the concept about linear independence and dependence. So let's try to solve a problem, okay. The question is saying that examine if these vectors, so you can imagine this is my alpha 1, this is my alpha 2 and this is my alpha 3. So I have three elements, alpha 1, alpha 2, alpha 3, and I need to examine whether it is linearly dependent in R3, okay. R3 means the set of all three-dimensional coordinates. So that means our first starting statement, as I told you, it's going to be something like this, which is equation number 1. Whenever a set is given to me, I need to consider equation number 1, then check whether this case is happening or that case is happening, accordingly linearly independent or dependent, okay. So first of all, I'll take the starting statement, which is number 1. So let me take the starting statement, which is C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3. So in this case there are three elements, so stopping at alpha 3 and considering this to be equal to 0, okay. So now just putting the values of alpha 1, alpha 2, alpha 3, this would turn out to be C1 alpha 1 is 2 1 1, C2 alpha 2 is 1 2 2, C3 and alpha 3 is 1 1 1, and in R3, okay, theta belongs to R3 obviously, so in R3 the theta null element is basically 0 0 0, okay, the 0 element is 0 0 0. So you can see I can form three equations from here. So multiplying C1 with the first x coordinate, C2 with the x coordinate, C3 with the x coordinate, and taking the x coordinate, the first equation would be 2C1 plus C2 plus C3 equals 0. Similarly, now if I take the y coordinates, I will have C1 plus 2C2 plus C3 equals 0, and another one if I take C1 plus 2C2 plus C3 equals 0. So you can see these are the three equations I'm getting from this one, okay. So multiplying correspondingly, I'm getting three equations, but you can observe one thing, that these two are the same equations written two times. So multiplying the y coordinate and multiplying the z coordinate is giving me the same equation two times. So basically this entire thing can be reduced to two specific or two unique equations, the first one and just one of these two. So that means I have the two unique equations looking like this, the first one and the one combined with second and third, which is C1 plus 2C2 plus C3 equals to 0. So the system of equations is reducing to only these two equations, okay. So now let me try to solve C1 and C2 and C3 and try to see whether all are specifically 0 or at least one of them can be non-zero, okay. Okay, so let's try to solve this in a cross multiplication way, which is C1 by, C2 by and C3 by, okay. So if I just look at it in this way, if I move out C1 from the picture, then I'll have to take the determinant, okay. So that would be 1 into 1, which is 1, minus 1 into 2 minus 2, right. So I'm getting 1 minus 2, so I'll just write that here, 1 minus 2. Similarly, if I move out C2 from the picture, okay, so for the C2 case we need to keep a minus sign, so I need to multiply this with this and this with this, so that would be 2 into 1 minus 1 into 1, so it will be 2 minus 1. Similarly, if I cancel out C3, it's going to be this into this minus this into this, so 2 to the 4 minus 1 into 1, so I'm getting 4 minus 1, and let me say that let this be equals to k, okay, where k is some constant, okay, any constant. So that means I am having C1 by minus 1 equals to C2 by minus 1 equals to C3 by 3 equals k. So that would give me that C1 equals to minus k. So I'm multiplying this with this, this with this, and this with this. Okay, so I'm multiplying all the fractions with the k. So C1 equals to minus k, C2 equals to minus k, and C3 equals to k. So I've got my answer in terms of k. Now here you can see that it is not mandatory that k has to be 0. See, if k equals to 0, okay, now imagine k was any constant. If k is equals to 0, then what is the solution I'm getting? C1 0, C2 0, C3 0. Now as I told you, all the constants are 0. This is an obvious solution. This is always there. Okay, this is always going to be there, that all the constants are 0. The main question is that the only solution, or other than that, do I have any other non-zero solution also? Okay, so now if k is 0, then all the constants are 0. So that's one obvious solution which is there. Now is that the only solution? Imagine if I take k equals to 1. Okay, I can take any value of k. K is any constant. So any non-zero value of k if I take, suppose k equals to 1, 2, 3, whatever, the values of the constants are all going to be non-zero. Okay, my definition was I needed to have at least one of the constants non-zero. If at least one is non-zero, it's linearly dependent. In this case, I'm getting, if k is non-zero, then all the constants are non-zero. So that means at least one non-zero is automatically satisfied. So I can say that if k not equals to 0, then we get non-zero Ci. If I call this equation number 1 satisfying equation number 1. Okay, so here if I take k non-zero, I'm getting solutions where the constants are non-zero, at least one. I need to have at least one, but here I'm getting all are non-zero. So I'm getting the constants non-zero which satisfy equation number 1. So that means the definition of linearly dependence has been satisfied. So this implies the given set S is linearly dependent. Okay, so that's how we do the proof. So this is the traditional way of doing the proof. That means using the proper definition of dependence. But we could have done this in a different way also. Okay, more faster and convenient way. But you need to remember, it's going to be restrictive. You cannot use this new way which I'm going to tell you for every problem. There are some specific cases where you can use this. Now, what are the specific cases? If your vectors are, suppose your vector, each vector is how many dimensional here? 3-dimensional vector. So 3-dimensional vector, 3-dimensional vector, 3-dimensional vector. How many 3-dimensional vectors? 3 3-dimensional vectors, right? Alpha 1, alpha 2, alpha 3. So there are 3 vectors and each vector is 3-dimensional. So I have 3 3-dimensional vectors. Okay, so if this 3 and this dimension, if the number of vectors and the dimension of vectors, if they match, okay, if they match, then there is a shortcut way of doing these kind of problems. Okay, but remember, if they don't match, okay, if they don't match, if suppose I have four vectors and each are of 3 dimension, then the method which I'm going to tell you, it's not going to work out. Okay, then you have to go by the normal definition method. Okay, but only if the number of vectors and the dimension, for example, again another example would be I have 1 0 0 1. If this was my set, okay, so this is a 2-dimensional vector and how many vectors are there? 2 vectors are there. So 2 vectors each of 2 dimension. So again it's a matching case. So again I could have used the method which I'm going to tell you for this example also. Okay, so now coming to the method which I'm talking about. When the dimension and the number of vectors match, just take the determinant, okay, which is 2 1 1, the determinant of the elements. Okay, 1 2 2, 1 1 1. Just take the determinant. Now why was I telling you that you can use this only when the dimension and the vectors match? Imagine I have 1 0 0 1 2 3. So each of the vectors are 2-dimensional and how many vectors are there? 3 vectors. So 3 vectors each of 2 dimension. So there is a mismatch of the numbers, 3 vectors 2 dimension each. So if there is a mismatch, the problem is you cannot take a determinant. Okay, suppose you take the first element 1 0 0 1 2 3. So that's not a determinant. A determinant has to be first of all a square matrix. Only then you can take a determinant of a square matrix. So it's not square. So because of the dimension and the number of vectors mismatch, you are unable to take the determinant. That's the problem. So in that case, you have to go by the normal definition. Okay. But as long as the dimension and the number of vectors match, you simply take the determinant. If the determinant turns out to be 0, okay, in this case I'm not going into the detailed calculation. Okay, I can do it, but just it will take me 2 more steps. Suppose I'm adding the elements r1 dash equals to r1 plus r2, then that would become 3 3 3 1 2 2 1 1 1, and now if I do the calculation that r1 dash equals to r1 minus 3 times r3, then it would become 0 0 0 1 2 2 1 1 1, and the value of the determinant would be 0. So if you just expand the original determinant, you are going to get 0 as the answer. So if you get 0 by taking the determinant of the elements, the conclusion is the given set is linearly dependent. Why? The concept is the elements depend on each other. When the elements depend on each other, proper row operations would help you to get a complete 0 row. Getting a complete 0 row means getting the determinant value 0. So now in the back calculation way, I can say if determinant is 0, that means the rows, the 3 rows that I have, they are somehow interdependent on each other. That's why I could get a 0 row. So if the rows are interdependent, now the rows are made up of the elements. That means the elements are interdependent. So the elements are interdependent actually means they are linearly dependent. Okay. So from now on, remember, if you have number of vectors and dimension matching, take the determinant. If the determinant is 0, then it is linearly dependent. If the determinant is non-zero, then it is linearly independent. Okay, the idea being same, that you cannot get a 0 row. In case of independent, you cannot get a 0 row because the rows are not depending on each other. That means the elements are not depending on each other. That means the elements are linearly independent. So this is a shortcut process if there is a dimension and number of vectors matching. Otherwise, you have to go by the definition. Okay. Now moving on to a theorem which is saying that given a set of vectors, okay, so a set of n vectors is given to me in a vector space over a field F, and that is supposed to be linearly dependent. If the set of vectors is linearly dependent, then this word is important, at least one of the vectors of the set can be expressed as the linear combination of the remaining elements. Okay, so given a linearly dependent set, then at least one of the vectors can be expressed as linear combination of the remaining others. Okay, so if I go back to the previous example, you will understand it much more better. In this example, see, I had shown that this given set alpha 1, alpha 2, alpha 3, this was linearly independent. That means this set is linearly dependent. That means using this theorem, I can express at least one of the vectors as a linear combination of the others. Okay, so how can I do that? In this particular example, if you observe carefully, that if I do alpha 1 plus alpha 2, that would give me 3 3 3, so which is equals to 3 times alpha 3, right? So alpha 3 is 1 1 1, so 3 times alpha 3 would be 3 3 3, and alpha 1 plus alpha 2 would be 3 3 3, right? So that means alpha 3 can be written as 1 by 3 times alpha 1 plus 1 by 3 times alpha 2. So it's basically looking like alpha 3 equals to C1 times alpha 1 plus C2 times alpha 2. So that means one of the vectors, so here C1 is basically 1 by 3 and C2 is 1 by 3. one of the vectors can be expressed as a linear combination of the remaining. The remaining is alpha 1 and alpha 2 in this case. Okay. So the theorem that I'm going to do, you can already see it's happening over here in this example. Okay. So now we want to prove this in general. Okay. So let me use up this information that this set is linearly independent. So first of all, let me name this set as the S set. Okay. So S is linearly dependent. Then if I consider this statement, like going to the definition of linear dependence, alpha 1 C1 alpha 1 C2 alpha 2 plus dot 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 Cn alpha n equals to theta. If I take this statement, okay, so I shouldn't start with then. I'm considering this statement and calling it number 1. Then at least one Ci must be non-zero, right? This was the definition of linear dependence. Okay. So let me consider that let some specific Cj is not equals to 0. Okay, some specific index j is non-zero. Okay. So that means this expression I can write as C1 alpha 1 plus C2 alpha 2 plus dot dot Cj alpha j plus again going on and until I reach Cn alpha n equals theta. So I have specifically taken that this Cj is something which is non-zero. Okay. So now if Cj is non-zero, I can say that Cj inverse exists in the field, right? Because if I take the inverse of a non-zero element, it's definitely going to exist, because if some element is 0, I don't know, the inverse will actually not exist, like the inverse of 0 element does not exist in the field. But any non-zero element, its inverse is definitely going to exist in the field. And what would be the property of Cj and Cj inverse? The property would be that if I take the multiplication of Cj with Cj inverse, the product would become 1, right? Multiplication of any element with its inverse would simply give us 1. Achha. So keeping that observation in mind, let me keep Cj alpha j on one side of this equation and take everything else on the right hand side. Okay, so I'm taking everything else on the right hand side. So I have minus C1 alpha 1 minus C2 alpha 2 dot 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 like this. The element just before this one would be Cj minus 1 alpha j minus 1, and the element just after this would be Cj plus 1 alpha j plus 1, and like this it would go on until Cn alpha n. So minus Cn alpha n. So I have kept this Cj alpha j on one side and taken everything else on the right hand side, so no need to write the theta on that side anymore. Okay, so something like this we are getting. Achha. Now I'm multiplying the element Cj inverse on both sides, because Cj inverse exists, so I can multiply it. So if I multiply Cj inverse on both sides, so I have Cj inverse Cj alpha j minus or equals to, sorry, minus of Cj inverse C1 alpha 1 minus of Cj inverse C2 alpha 2 minus of dot dot Cj inverse Cj minus 1 alpha j minus 1 minus of Cj inverse Cj plus 1 alpha j plus 1 minus dot 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 minus Cj inverse alpha n Cj inverse Cn alpha n, right? Cj inverse Cn alpha n, right? So I have got this kind of an equation where I have multiplied the entire equation by Cj inverse on both sides. Now you can observe that this part is going to become simply 1 from the thing that I have written here. And let's say these things are some elements of the field, okay, some constants. I can give it some new name. I can call it, let's say, P1. This one I can call it as P2, this one is Pj minus 1, this one is Pj plus 1, including the minus sign, pj plus 1, and finally this one is pn, right? So if I just rename these elements just in order to make it look much more better, so on the left hand side I have only alpha j, on the right hand side I'm calling this one as p1, then the next one is p2. So like this, when I reach the j minus 1th element, it's going to be pj minus 1 alpha j minus 1, then the next one would be pj plus 1 alpha j plus 1, and like this, when I reach the last element, it's going to be pn alpha n, right? So I have got this kind of an expression, and just see, this is the one that I wanted. Okay, what was the statement telling me? The statement was telling me that, the statement was telling me that at least one of the vectors can be expressed as a linear combination of the remaining others. So here one of the vectors, which is alpha j, it has been expressed as a linear combination of the remaining other elements. Remaining other means alpha 1, alpha 2, all the elements except alpha j up till alpha n. So alpha j has been expressed as a linear combination of its remaining others. So hence it's kind of proved, right? So now we could have done this conversely also. Okay, so I won't go into the conversely part. Okay, you can very well understand the conversely part. Conversely part, what you will do, you'll start from this line, go up to this one, go up to this one, go up to this one, and finally reach the first line. So just it would be a back calculation. Okay, so conversely part, just we can go one step up every time and reach the same starting point again, that if any element can be expressed as a linear combination of remaining others of a set, then that means that set is linearly dependent. Okay, right from where we started. Okay, so the conversely thing can be done just by going one step backwards each time. Okay, so that's about this theorem, and we complete this part and see you in the next lecture.